In this video, we are going to expand our view from simple microscale, mesoscale, and synoptic scale meteorology, and we're going to go global scale and look at general global circulation patterns. Now, this gets a little more complicated because there's so much that happens on the global scale. It is very hard to just identify one simple pattern that causes things to happen. So we start looking at average conditions to help us identify the driving forces of global wind patterns. Now, we can tell that the basic cause for general circulation is really just a thermal circulation, like we've talked about a couple of times in this chapter already. Warm air is transferred from the tropics to the poles, and cool air from the poles to the tropics. And this drives most of the atmospheric circulations on a global scale. Now, to understand it more completely, we need to simplify our understanding of the Earth. So we're going to make a few assumptions to create a basic model of what happens, and then we'll get rid of these assumptions one by one, and then we'll have a full picture of what happens on the Earth. These three assumptions are that, first of all, the surface is just a uniform water surface. Second of all, the sun is always overhead at the equator. And third of all, that the Earth does not rotate. Obviously, these are ridiculous, but they help give us a starting point to understand what happens. Now, when this happens, when we make these assumptions, what we find is that we end up having heating right over the equator with rising motion. And then when that air rises, it then pushes towards the poles, thus see that the hot air is being pushed towards the poles. Then you have sinking motion over the poles, bringing the cold air back towards the equator. And so you have a great big thermal circulation. This is what we call a Hadley cell. Now, kind of ridiculous, but what we notice is when we take away the third assumption that the Earth does not rotate, instantly things become a little more realistic. When the Earth starts to rotate, then this Hadley cell actually breaks up into three cells. The first is the Hadley cell. Instead of going from the equator to the poles, it only goes from the equator to latitudes of 30 degrees. And then you have the Ferrel cell, which is a circulation in the opposite direction, but between the 30 and 60 degree latitude lines. And the polar cell, which is between the 60 degree latitude line and the pole itself. Okay, so a couple of things to note here. In the Hadley cell, notice that the winds along the surface are going from the 30 degree latitude towards the equator. Well, when you kick in the Coriolis force turns things to the right in the northern hemisphere or to the left in the southern hemisphere, creating winds that are coming from the northeast in the northern hemisphere or from the southeast in the southern hemisphere. And so these are called the northeast and southeast trade winds. When people would sail from Europe to the New World, they would often follow these trade winds because they would blow them towards the west, where the Western world is located. Now, if you go, one more thing before I move on. Notice how the winds converge in an area right around the equator. They converge with a lot of rising motion, creating a lot of storms. This region is called the doldrums. That's the common name for it. The official name is the Intertropical Convergence Zone, or the ITCZ. Now, the reason this is called the doldrums is winds will be pushing you towards the equator, both from the north and the south. So unless you're a very skilled sailor, ships would often get stuck within the doldrums, and it would be very, very difficult for them to move out. All right, that does it for the Intertropical Convergence Zone. Now let's look at the Ferrel cell. In the Ferrel cell, the surface winds are moving from the 30-degree latitude line to the 60-degree latitude line. Once again, the Coriolis force turns things to the right in the northern hemisphere. Thus, the winds between 30 and 60 degrees latitude generally go from the west to the east. So we call these the westerlies. Note how a lot of the major weather patterns that we have in the United States move from west to east. This is precisely why, because they follow the westerlies. Now, the polar cell, you've got winds going from the poles towards the 60-degree latitude line. And once again, that creates an area of convergence over the 60-degree latitude line, creating a region of typical storms. This is what we call the polar front. It's also where we often see what we know as the jet stream. In all actuality, there's more than one jet stream. That's for a future video. But when we talk about the jet stream, it is a fast-moving current of air over the polar front. Okay, so that creates areas of storms at the equator and at 60 degrees latitude. But what's happening in between the Hadley and Farrell cells? Notice how the air from both cells at 30 degrees latitude is dropping, sinking towards the surface, which means you don't get a lot of cloud development. In fact, you get no cloud development at all, and you get very hot and dry regions because you don't have any cloud development. Well, take a look at this. This is kind of interesting. Over the equator, you have the rising motion of the Hadley cells. At 60 degrees latitude, you have the rising motion of the polar front. And at 30 degrees latitude, you have the sinking motion between the Hadley and Farrell cells. Over the equator region, you have this nice, lush green area where you get lots of rainforests. Over the 30-degree latitude line, sinking motion, not a lot of precipitation, not a lot of clouds even. You get a lot of deserts. Think of all the deserts you can think of, the Sahara Desert, the Middle East, the Death Valley, the South Africa, the deserts of South America, Australia. All of them are located right around 30 degrees latitude. And that is precisely because the air between the Hadley and Farrell cells is sinking at 30 degrees latitude. Here is a figure from your textbook showing the ITCZ, the Intertropical Convergence Zone. Basically, you see a big line of thunderstorms. Let's see if we can see this current live image here. Here we go. Got it. Unfortunately, right now, we don't see much of an intertropical convergence zone. It's kind of not there right now. Usually we get some. All right. So what we would see if we saw an intertropical convergence zone is just a line of thunderstorms, very solid thunderstorms, right around the equator somewhere. Looks like we have a bit of an ITCZ right here, plus some storm system dropping off here to the south. So it looks like we might have some ITCZ going on right there. All right. Of course, 30 degrees latitude, typical latitudes for your subtropical highs where we get deserts. Okay. So this helps to indicate some average wind flow patterns. However, this itself also changes. Remember, we made three assumptions. The first was that the Earth was only made of water. The second is that the sun is always overhead at the equator. And the third, that the Earth doesn't rotate. We got rid of the third assumption. We have this model. Now let's get rid of that first assumption, that the Earth is just made of water. So now we'll reintroduce land. And what we've noticed is very consistently, you get low pressure systems around the equator. high pressure systems right around 30 degrees latitude, and low pressures right around 60 degrees latitude with highs around the poles, which is roughly what we see here. So you've got high pressures right around 30 degrees latitudes, lows around 60, and highs around the poles. Not perfect, but that has to do with the fact that the Earth is no longer just plain water. When you introduce land, that causes friction, slows down winds, and distorts these patterns that we are used to, that we saw in this figure right here. Now we can get rid of the other assumption as well, that is that the sun is always overhead at the equator. We can look at this is the typical map for January. You can see what happens as we move towards July. Everything moves to the north. The ITCZ is at 0 in the southern hemisphere in January, but in the northern hemisphere in July. Also notice here over Asia, good example of something here. The Siberian high is a good driver of something we talked about in a previous video, the katabatic winds. But then that's replaced later on with a thermal low, bringing in some very wet, moist air, which we call the summer monsoon. All right. So here are the two figures together just so you can compare them side by side. Now, these semi-permanent highs and lows let me go back and tell you about semi-permanent highs and lows. All of these highs and lows in these figures are what we call semi-permanent highs and lows because we tend to see these high and low pressure systems fairly frequently. Here are two that affect us. You have the Pacific high and the Bermuda high. The Pacific high, obviously in the Pacific Ocean, tends to bring cold, dry air from the north, whereas the Bermuda high brings wet, moist air from the south. So you have semi-permanent highs on both sides of the United States, but they bring very different weather into the two coasts. And that's just an example of how these semi-permanent high and low pressure systems can affect normal everyday weather.